Today we're going to talk about this concept called random variables, okay, discrete random variables. And so up to this point, we've kind of talked in a general way about what the sample space for an experiment could be, right? I could flip a coin and count the patterns of heads and tails, right? So for example, one sample space could be 2 flips of a coin, and I get, you know, these are my 4 possible outcomes, right? This is my sample space. I could do an experiment, and I could obtain a success or a failure. Or I could flip a coin 3 times, and I could ask, how many heads did I get, okay? Now, we're all more or less engineers, right? And so at some point, you know, to really be able to dig into probability for engineering applications, right? That's what the name of the course is, or I guess it's called engineering probability. You know, you can't really go too far with analyzing just experiments like this that have these kind of like symbolic outcomes, right? Eventually, we need things to be numerical, right? So from today onwards, we're going to be basically talking about experiments that generate some sort of a numerical result, a numerical attribute. So all of our sample space outcomes are going to be real numbers, right? And the advantage of this is then we can start talking about things like means and variances and things like that that you may vaguely remember from statistics classes or high school or something like that, right? And that's really important. We need to be able to understand the outcomes of experiments and analyze them in a more numerical, statistical fashion, okay? So to summarize that, in most engineering applications, we care about some numerical attribute of the outcome. Right? And in these cases, it's not hard for me to assign a numerical attribute to these experiments, right? So for example, in the first experiment, I could say, okay, give me the number of heads, right? That's a way of converting this kind of symbolic sample space to something that gives me a number, 0, 1, or 2. In the second case, I could say, well, I'm going to assign a 1 to a success and a 0 to a failure, right? So I've kind of turned this from a word problem into a binary problem. And the third case, I'm already in a numerical sample space, so there's nothing left for me to do, right? And so a random variable, this is a kind of the key concept of today. So a random variable. So this is a little bit more wordy than it has to be, perhaps. But in words, it's basically an experiment that gives us a number, right? That's the big picture, okay? So let me write this down a bit more officially, right? So a random variable x is a function that assigns each outcome. And again, I'm going to use this kind of like curly, this is a zeta. Either zeta or an eta. Doesn't really matter. It's like a curly s. Each outcome in the sample space to a real number. X of this. So it's like saying I have a function that goes from the sample space, no matter how I describe those experiments, to some real number, right? That's what this fancy R means, okay? So for example, if I take this guy over here, so for example, suppose that my sample space is the pattern of 2 coin flips. My function x could basically be, you know, kind of in words, it would be like count the number of heads. And that would mean that I kind of have a mapping that says, okay, so if my outcome is given on the top, then the results are at the bottom, right? So my x value is 2 in this case, and 1 here, and 1 here, and 0 here. Right? So if I think about it, it's kind of like a graph, or it's like a mapping. So I have some sort of like, we've been drawing these kind of cartoony sample spaces where this is my sample space S. I take some outcome here, and then every outcome gets mapped via some function down to the real line, right? And that value that it lands at is this x. Okay? Simple idea. And so what we're going to talk about today is situations where, you know, this outcome gets mapped to a discrete set of values, meaning 1, 2, 3, 4 values I can count on my fingers, right? So a discrete random variable x is a function from some generic sample space S to a discrete set of values on the real line. So pretty much all the examples that we're doing in class up to this point are going to be kind of discrete random variables, okay? But there are many that are not. So in some sense, the division line is exam 1, right? So basically everything before exam 1 is discrete, everything after exam 1 is continuous, okay? And so for example, you know, if I say, okay, what's the, you know, temperature outside, that is a continuous random variable because the temperature could be 73.8952, right? It's not, you know, a chunk of thing. Question? I see some confusion. On the real line. Yeah. So what I mean by this statement is something like this, right? So I have, you know, my sample space. Again, let's go back to that example. Here's my sample space. Here are my possible outcomes. And then here is my real line, and here are my discrete set of values, 0, 1, or 2, right? So basically, this is the result of applying the function to tail, tail. This is the result of applying the function to either tail, head, or head, tail. And this is the result of going from head, head, right? So this guy is going to here, this guy is going to here, this guy is also going to here, this guy is going to there, right? Now, what matters here is that there are basically a countable set, right? I can kind of start counting them off of my fingers, 0, 1, 2, 3, right? So discrete doesn't necessarily mean finite, right? So if there are only 3 options like this, then that's great. I could also have a discrete random variable that gets mapped to an infinite number of possibilities, but there's still things I can count on my fingers, right? So for example, I could say, you know, or I could say, flip a coin until I get tail, record the number of flips it takes. Right? So here, I have to flip the coin at least once. I could require 1 flip, 2 flips, 3 flips, 4 flips. So basically, you know, I have an infinite number of flips it could take, but I can kind of start enumerating these possibilities, right? Bless you. Okay. And so, simple concept. Let me just pause and ask any questions about this. Okay. So this is kind of like going from possibilities, outcomes in the sample space to these values of this random variable x, right? And now we can start talking about events, right? So we kind of have been talking about events so far. So we can say, events in the original sample space map to basically regions of the real line, right? So for example, you know, I could say something like, in this case, if this is my, you know, if this is my random variable, so let's say my sample space here is a tail and then I stop, or head and then tail, or head, head, tail, and so on, right? So this is kind of like the raw sample space, and then this gets mapped to here, and this gets mapped to here, and so on, right? So then I could say something like, you know, the probability that x is, say, less than or equal to 3, that's a question about this numerical random variable, right? And that's kind of, if we want to be really pedantic about it, we could say that's like the probability that the mapping of this outcome was less than or equal to 3, which is like the probability that my outcome was equal to tail or head tail or head head tail. Right? So this is basically, you know, this is like a subset of S, which is like what we've been calling an event. And this here is like a subset of real numbers, subset of the real line. And to make it even more belabored, right? So basically I could say it's something like this. You know, I have in the, so let me say the random variable introduces what we called a partition on S. Right? Remember what we called the partition was basically a bunch of subsets of S that are all disjoint, no overlap, but together make up the whole thing, right? And so I could say, okay, you know, if here is my sample space, I could make a set that says, okay, all of these outcomes over here in this part of the sample space get mapped to this one value over here. And all these guys get mapped to this value over here. And so on. Right? So here, basically, this AI is just like the set of outcomes such that the real number that I get by applying my function is xi. And so, in some sense, what I'm saying is, show me all the things in the sample space that map to 1. Now show me all the things in the sample space that map to 2, and so on. If I look at all those possibilities, I have carved up the sample space in terms of the real numbers that they map to, okay? And kind of conversely, then I can use kind of this thing on the right to say something along the lines of saying, okay, you know, what's the probability that, for example, if I have a real line and say these are some possible outcomes, I could say, okay, if this is my world of X and I want to know what's the probability that I'm in this range, I can map that back into S to asking about what are the probabilities of, you know, the stuff in these two events, A1 and A2, right? So I could say something like, you know, the probability that X is in the range, you know, 1/2 and 5/2 is the same as the probability of A1 or A2 happening, right? Which, since this is a partition, is just like the sum of these two events. Okay? I mean, in some sense, this is all, in my opinion, a little bit tedious. I mean, the key idea is, right, I'm taking some outcome and I'm turning it into a number, right? And then all the stuff about probability that I've talked about for the past 4 lectures that has to do with generic sample spaces and events and so on gets kind of inherited by these actions on the numbers, right? To the point that we don't even necessarily have to worry about this intervening sample space. We could just jump right to saying, okay, I've got an experiment, and from that experiment, I derive a number, right? So in some sense, we can kind of remove that middle layer of the outcomes that may or may not be numbers at all, right? Okay, so let me pause and ask. Questions or comments about this? Let's make this a little more concrete with some more examples. So the key idea here is that now what I'm saying is that I do an experiment, and the result of that experiment is a number, okay? And now, just like I defined some rules about the probabilities of events in the sample space, I can be more explicit to say, okay, so how do the probabilities shake out in terms of where they lie on these possible points that I could get as outcomes, right? So the key concept going forward is what's called the probability mass function, okay? So this is a really foundational thing. Or PMF. So the PMF of a discrete random variable is basically just a chart or a list of, for each possible numerical outcome, what's the probability of getting that outcome? Super simple idea, right? So the PMF of a discrete random variable and you may see me start to abbreviate this as RV just for laziness. X is defined as this special notation, okay? So it's little p. I'm going to make this note for a second here. This is kind of hard to tell when it's not typeset. So this is little p, big X, little x, okay? It doesn't help that capital P's and little p's and capital X's and little x's both look the same, but that's why I provide this helpful guide, right? This is just saying the probability that the random variable has this numerical value. And again, to be really tedious, I could say it's the probability, looking back at the original sample space, of the set of outcomes such that the mapping from the original sample space to that outcome is equal to x. And I can ask about this for any x in the real line. Now I said that the setup for today is that x is discrete, right? That means that I can only get one of a countable set of possibilities, right? So since here x is a discrete random variable, this probability mass function is only non-zero at a set of values, set of numbers, x1, x2, x3, and so on, right? These are the places where I could get the result, right? So in some sense, you know, we could go right to thinking about a new sample space, which is basically this set of outcomes from the get-go, and assign consistent probabilities to every one of those numerical possibilities, okay? And so, you know, to jump ahead before I start drawing things, you know, the PMF is basically kind of like a bar graph of, for each of these possible places, how much probability is there, right? Now this bar graph has to basically add up to 1. It has to satisfy all the same kinds of probabilistic rules that we laid out in lecture 2, right? So things like you can't have negative probabilities. All the probabilities have to add up to 1. if you have different, disjoint sets of outcomes, I get the results by adding up the result of every outcome, right? So let me just say that mathematically. I just kind of said it in words, right? So basically, the PMF basically has to satisfy a bunch of properties that are inherited from the axioms of probability. Right? What do I mean by that? So for example, the probability of any event, I already told you a while back, has to be non-negative, right? So for example, one of these rules is that the probability of any outcome has to be greater than 0, greater than or equal to 0 for all x. Right? This just means no negative probabilities. Also, if I add up all the values of this probability mass function, basically it's like I'm adding up all the pieces of the sample space, and that has to add up to 1, right? So if I add up for all of the values that this random variable could take on, the values of the PMF, basically this is like saying I'm adding up in the original sample space all of the probabilities of these events, right? Remember that it's kind of like this picture, right? All of the places, so I'm saying I want to add up the probability of this, plus the probability of this, plus the probability of that. That's the same as adding up the probabilities of these big events back in the sample space. Since they don't overlap and they comprise the whole thing, that means that this whole thing has to add up to 1, right? So basically, the PMF values add to 1. One of those things has to happen, and that makes up all the probability, right? And then if I say, okay, for a event, so the probability that x is in some set, now remember, this is a real number now, so this is like kind of a subset of the real line. This is basically the same as I look in that region and I add up all the places where the outcomes are in that line, right? So that's kind of like saying, okay, if I want to know, here's my set of possible outcomes on the real line, and I want to know what is the probability of kind of like this subset, all I have to do is add up the 4 probabilities that lie inside that shaded area, right? Which I think is, it's almost, stands to reason, right? Okay. So again, this is really vague, so let me try and make this a little more concrete, right? So far in this class, we talked about a bunch of different random variables without you really knowing it yet, right? So we talked about what would be the outcome of rolling a fair die, right? That's one. We talked about, keep on flipping the coin until you get heads. That's another kind of random variable. We talked about flip the coin n times and count the number of heads that you got. That's a third random variable, right? And there are other ones that don't fit into that formalism that we're going to talk about a little bit more, okay? So let's talk about some types of random variables, okay? So, and now the nice thing is that, we specify a random variable by basically telling you what the probability mass function is, okay? So now I can just draw a picture and say, here's a random variable. Let's talk about it, right? So now we introduce some key random variables, some key discrete random variables by specifying their probability mass functions. So, simplest one is the uniform random variable. This is the one that you're probably most used to. So basically, in order to talk about the uniform random variable, I need to actually give you kind of like a range, right? I have to say, okay, what are the values that I'm talking about? Am I talking about a 4-sided die or a 6-sided die? Okay, so so basically, a uniform random variable on the list of numbers 1, 2 through n is specified by the PMF 1 over n for x in these set of possibilities, right? So this is exactly like rolling the 6-sided die, and I say, okay, the possible outcomes are 1, 2, 3, 4, 5, 6, and the probability of each of those things is 1 over 6, right? So this is just exactly like a fair 6-sided die. Okay. Now, if I wanted to draw this PMF, how would it look, right? So I have 6 possibilities, and I draw 1/6 over here, and I'm going to draw it like this. Now you're going to ask yourself, what is up with this arrows? Now, since this class is a prerequisite with signals and systems, you know what that means. This is a delta function, okay? Oh, not good. I promise not to belabor this, but you know, there's a reason why I'm drawing it with arrows, right? So you can think about this as drawing it like a bar graph or a histogram. That's okay. But when you see me draw PMFs, and when I ask you to do PMFs on the homework and on the exams, I'm a little bit persnickety, so I would like you to draw them with delta functions, okay? And the reason for that is, as a preview, right? So, you know, these arrows, right? This technically is what's called a delta function, right? So why would I do this? Why? Why would we draw it this way? Right, well, the preview is that if I wanted to ask about the probability that x is, you know, kind of like less than some number, for example, right? If I did it in this way, I could think about this like I integrate from -infinity to 2.5 of this thing, right? If I thought about this like a delta function, this would be like saying, okay, I'm going to integrate from all the way over here up until this point, and I'm going to talk about how much area I've accumulated up to that point, right? And we know from signals and systems that as I integrate over a delta function, I pick up an amount of area instantaneously that's equal to the height of this arrow, right? So it's kind of like saying, as I cross 1, I bump over and I've got 1/6 of the probability. And as I bump over the next arrow, I get another 1/6 of the probability. So this would be like saying I have, you know, 1/6 plus 1/6 is equal to 1/3, right? Now, this is, you know, kind of like, yeah, the way I introduce this is certainly here, just to be clear, when you talk about the PMF, we do talk about solid, real numbers, right? There's no delta function in this definition. And that's cool, right? I just like to draw it this way because coming down the road after exam 1, we're going to introduce this more general concept called a continuous random variable, right? And instead of there being something called a PMF, where I can only hit, you know, one of a certain set of possibilities, there's a continuous range, an infinite range of where I could be, right? And it turns out that if I think about the PMF as kind of like a preview of the PDF, that drawing these things as delta functions makes a little bit more sense. Now, I don't know, depending on what book you're using, they may not draw it this way, they may just use bar graphs, and that's okay. But this is just me getting you primed for the harsh reality that after exam 1, you're going to be doing a lot of integration, okay? So it's a good time to kind of, you know, like over that homeworkless time after exam 1, just start doing some integrals. You know, you're gonna need those integrals coming up, okay? But For the moment, just say, okay, he's making me draw these delta functions. I'm just going to take it on face value. But this is kind of like, for those of you that are wondering, that's why, right? So this is kind of like generalizing to this concept of PDFs, okay? Okay, so this is one. We learned either the last time or the time before about what we called Bernoulli trials. I think that was just last time. Or Bernoulli random variable, sorry. Right? So a Bernoulli random variable is basically very simple. It just maps success to 1 and failure to 0, right? So in order to specify a Bernoulli random variable, it's just something that either is 0 or 1, right? And so that says the probability of failing, I'm going to say, is 1 minus p. The probability of succeeding is p. Those are the only two options. If I were to draw it, that's just saying I got 0 or 1, and these arrows have to add up to 1 in total, okay? Super simple. Okay, and then we talked about some things that we could kind of extract from the Bernoulli random variable, right? So we talked about what happens if I do a whole bunch of independent experiments and I add up the results, for example, right? So that would be what we call a binomial random variable, right? So a binomial random variable is basically the number of successes in n of these Bernoulli trials, right? So in this case, this is like saying the probability of exactly k successes in n trials. And we looked at this formula last time, right? This is like saying, okay, in order to succeed exactly k times, that means I have the probability of success to the k power. I had to fail n minus k times. And then I had to ask myself, how many ways were there for that to happen, right? There are n choose k ways of those successes being distributed across the n slots, right? And the number of possibilities, either I could have 0 successes, 1 success, all the way up to n successes. And so if I were to draw this, this is exactly like the Plinko that we were showing last time. This would be like saying, let's suppose that n equals 6, and the probability of success is 1/2. So this is kind of like a, you know, flipping a fair coin. So my outcomes are from 0 to 6, and it's not that likely that I get only 0 and not that likely that I get all heads. And so basically a, you know, binomial random variable kind of looks like this, right? Something that is generally peaked in the middle and falls off towards the edges, right? And if you remember the Plinko example from last time, if p is a lot bigger than 1/2, then I'm much more likely to get ahead. And so that means that the bulk of this distribution will be kind of shifted over to the right-hand side, right? I'll get a lot more heads on average than I would have with a fair coin, right? All right, so let me pause and ask. Any questions so far? I mean, really, I'm not telling you anything that you didn't already know. I'm just talking about a different way to describe it, right? So certainly, so far, I've asked you to do these kinds of computations, and it hasn't been a big deal, right? All I'm telling you now is that these numbers, these probabilities, are actually elements of this probability mass function, right? So just giving a new name to hopefully an existing concept. And then the other thing that we talked about was the idea of flipping the coin until something happens, right? So a geometric random variable is basically the number of Bernoulli trials before a success. Right? So again, my possibilities are going to be, you know, my x of k's are going to be either 1 trial, 2 trials, 3 trials, up to a potentially infinite number of trials, right? So we kind of showed in a bunch of other cases that the probability of succeeding on the first try is p. The probability of requiring exactly 2 tries is I fail once and then I succeed. The probability of needing 3 trials is failing twice and then succeeding once. And so I can see the pattern, right? The probability of needing exactly n tries is going to be, or maybe let's just say this, k tries, I think would be better, would be equal to failing k minus 1 times and then succeeding on that next try. And so here, my possible values are 1, 2, 3, so on. Okay. Now you can see that in order to specify a type of random variable, so common exam question, right? I give you some sort of a real-world scenario, and I ask you, what kind of random variable is this, right? And you tell me, oh, it's a binomial, or it's a geometric, right? So kind of being able to identify what kind of experiment we're doing and name the corresponding random variable is like kind of, you know, probability 101, right? So for example, on the current homework, the one that you just turned in, right, you know, Thanos snapping until something happens is a geometric random variable, right? Because I'm waiting for an event, it may take me an infinite number of times, and I got the same independent probability every time, right? Now, when you are asked what is the, you know, type of random variable, it's good practice to tell me also the parameters that may go along with it, right? So if I ask you what kind of binomial, you know, what kind of random variable is it? It's a binomial. You should also be able to tell me what is n and what is p, right? So that kind of goes along with the idea of, okay, so, you know, in this case, you should tell me it's binomial, n equals 6 and p equals 1/2, right? So that I know exactly what you're talking about. Okay, so we stop and ask. Any questions or comments about this stuff so far? Okay, so let me just say, okay, you know, at this point, you may be wondering, man, you know, can everything in the world be boiled down to coin flips? And the answer is no, right? So now the PMF gives me an opportunity to talk about different kinds of distributions that are kind of arbitrary, right? So I could just tell you, okay, you know, here is a PMF, you know, kind of an arbitrary PMF. As long as everything added up to 1, things would be fine, right? So I could say, okay, the probability of getting 1 is 1/3, and the probability of getting 4 is 1/2, and the probability of 10 is 1/6, right? That doesn't look like anything that we've seen so far. Doesn't fit into one of our named, you know, categories, but it's perfectly fine, right? It obeys the rules, and it adds up to 1, and there it is, right? So I could talk about this like anything else. And this kind of also illustrates the point that there's no reason why the elements, you know, that I could get, the real numbers that I get, there's no reason they have to be in order, you know. If I wanted to, I could make a PMF that had, you know, and there's no reason they have to be integers either. I mean, it is, you're going to see all the time integers, but I could have something like this, you know, negative 25.3 with probability 1/2 and, you know, 78.4 with probability 1/2, right? This is still a discrete random variable because there are only 2 outcomes, right? And they add up to 1. It's okay if, you know, on the x-axis I've got some weird number, as long as I don't have so many of them that I can't count them on my fingers, right? So just to make it clear that this is okay, right? And the fact this is negative doesn't mean that I violated my rule about negative probabilities, because this is not a probability, it's a value, right? That's the value that something got mapped to. But I think it is fair to say that in most cases, you're going to be dealing with integers because we're trying to make life easy for you, okay? All right. So let me do a random variable that has a name that is a new one, okay? Let's do something new for once, okay? So a new one is called a Poisson random variable. Yes, like the fish. And so the motivation for this kind of thing is basically situations where events are arriving at a certain rate, okay? But the rate is kind of random. So for example, I've got customers who are walking into my front door in my store, or I've got packets that are arriving at a router, or I've got cars that are passing a mile marker on the freeway, or phone call attempts that are bouncing off of a given cell tower, or photons of light hitting a photodetector. All those things are kind of examples of, I basically got a timeline, and then I've got kind of little hash marks for when these events take place, okay? So the idea is kind of the motivation is events that occur randomly in kind of continuous time. Right? And I guess just for the sake of posterity, let me write down a couple of those things, right? So for example, customers arriving at a store, or packets arriving at a router, or cars passing a mile marker. I'm not going to write down everything. Right, so one of the first things I introduced probability with, I think in lecture 1, was, I've got a buffer, right? My router has a buffer, and it's collecting all the network traffic from all of the users in my dorm, for example, and there is a finite size that this router can store packets that are coming in and before it gets overflowed, right? So there's this kind of buffer overflow is a constant problem in designing some sort of real-world packet system, right? And so you can ask questions like, okay, what's the probability that my buffer overflows, i.e. that I receive more than 1 million packets in 10 milliseconds, right? And I model my network traffic to understand how my buffer should be sized to avoid this kind of problem, right? So what is the PMF here? Okay, so the PMF of this is it looks different. So what's happening here is that I've got a random variable. It can take on values from 0, 1, 2 off to infinity, right? And the intuition here is basically how many things happened within a given time period. Okay, so 0 things could happen, 1 thing could happen, 2 things could happen, and so on, right? And this alpha is equal to the observed average number of events in a given length interval. Right, so let's do the packet kind of example. So let's suppose that x is the random variable that is equal to the number of packets arriving, in a 10 millisecond window. Okay, so alpha, which is this parameter, is basically the average number of packets expected in this window. Right? So for example, I could just watch the dorms and I could just say, okay, every hour I'm going to record how many packets hit my router and I'm going to average that number up and that's going to be my alpha, right? That's kind of like my alpha per hour, okay? And then I could ask a question like, okay, so if this is a Poisson random variable, what is the probability that I have more than 4 packets in 10 milliseconds if my average value is 2 packets, okay? All right, so I can use the PMF to solve this problem, right? That's basically like saying, okay, what are my possible PMF values? 0, oops, 0, and he draws a 1. 0, 1, 2, 3, 4, 5, 6, and so on. So I want to know what's the probability that I get more than 4, right? That's like saying add up all of these numbers, right? And so hopefully by now you're getting used to the trick that if you're asked to add up a bunch of infinite things, maybe it's better to look at the flip side and say, okay, well, what I could do is I could just add up the probability of getting exactly 0, exactly 1, exactly 2, exactly 3, exactly 4, add those up and say 1 minus that, right? Because this smaller guy and this infinite guy make up the whole set of possibilities, right? So I'm looking at the complement of this set. So what is the probability that I get 0? Well, it's going to be, I'm plugging in 2. I have 2 to the 0 power over 0 factorial e to the minus 2, which is 2 to the 0 power is 1, 0 factorial is also 1, so I have e to the minus 2. Probability of getting exactly 1 packet is 2 to the 1 power over 1 factorial e to the minus 2, and then I get 2 e to the minus 2. Then I can keep on doing this, right? So I can say the probability of getting exactly 2 packets is 2 to the 2 power over 2 factorial e to the minus 2, which is 4 over 2, which again happens to be 2 e to the minus 2. And then this, 2 to the 3 factorial e to the minus 2 is 8/3, or 8/6, sorry, and so on, right? You get the idea. I don't know why I chose so many numbers. And what's that? 16 over 24 e to the minus 2. Right? And so if I think about what this looks like, so in this case, let's think about it. So that's like saying that the probability of getting 0 is e to the minus 2. The probability of getting 1 is twice that. The probability of getting 2 is, again, twice that. Probability of getting 3 is 8 over 6 is like 1 1/3, so it's a little bigger than I started with. This is now less than 1. And as I go forward, things will get smaller, right? So here I can see that, you know, if I compared this to something like a geometric distribution, give me 1 second. So if I compare this to something like a geometric distribution, if I go back to my geometric picture, if I can find it. So let's just compare this for a second to, I'll put this back in a second. So if I think about what does you know, geometric random variable look like, I think we covered this in a previous thing, right? So if I have, you know, one trial is p, then the next trial is p times 1 minus p. 1 minus p is some smaller number, right? So this number has to be less. Then I'm multiplying it by, again, some smaller number. So I know that for a geometric random variable, things can only get less probable as I go on, whereas for this Poisson random variable, what I get is something that kind of like goes up and then it goes down, right? So this helps me make a, you know, and versus the binomial, which is kind of symmetric, if I've got a fair coin around the middle, this basically is kind of like a different model for how things can arrive, right? And, you know, part of probability in the real world is understanding which random variable should map onto which problem, right? So it turns out that arrivals in the real world, like cars and packets and customers, generally can be shown to naturally follow this kind of Poisson rule, right? They don't follow a geometric rule. They follow a Poisson rule because that's just the way that the real world happens to work, right? So kind of a good rule of thumb is choosing the right random variable for a given problem. Question? The denominator of this fraction is basically k factorial. What am I? 6, right? Right, 3 factorial is 6. Right, so I have 2 cubed is 8, 3 factorial is 6. Okay. Okay. Questions or comments about this idea? So another kind of classic probability question is, I give you a Poisson random variable, So here, the way I set this problem up was to say, okay, let's suppose that I had a situation where, just going to put this back. So suppose I've got a situation where I have alpha equals 2. Okay, that's the number of packets that I expect in a 10 millisecond window. Okay, now suppose I ask you, okay, you know, what is the probability that I get exactly, say, 5 packets in 50 milliseconds? Okay. Now this is a little bit different because, you know, this alpha here is the alpha that's made for a 10 millisecond window, right? So if I have a 50 millisecond window, I have to use a different alpha. So here, alpha here is going to be, well, if I expected 2 packets in 10 milliseconds, then I expect 10 packets in 5 times. So if the interval is 5 times longer, then I should have 5 times as big of an alpha, right? And so the probability in this case is, you know, again, I look at my Poisson formula, right? My probability is alpha to the k over k factorial e to the minus alpha, right? Which I would have to multiply out. It would be something probably pretty small because e to the minus 10th is like super small, right? Because, you know, if you think about it, this is like saying, well, if I expected 10, then the odds that I get 5 is got to be pretty low, right? Because in general, I should be expecting more packets and not less, right? So definitely one of the homework problems is along the line of you have to adjust what your alpha is according to the interval of time that I'm asking you about, okay? Okay, let me pause and ask. Questions or comments about this stuff? Okay, so let me do a quick preview, okay, which is basically, so a couple more things I want to do. So, you know, a preview is, you know, if I don't know the PMF, we can estimate it by doing a lot of experiments, a lot of random experiments, and kind of aggregating the results. So by doing a lot of random experiments, and kind of aggregating the results. Right? So what I mean here is that I could just basically say, okay, if I want to know what is the probability of getting a certain value, I could say, what is the number of times that the random variable turned out to be xk, and I divide that by the total number of experiments I did, and that should kind of converge in the limit to the probability of xk, right? So it's kind of like saying that, you know, this is the difference between the rational, or not the rational, the real world, where I can keep on flipping that coin and look at what happened, and the purely theoretical world of probability, right? And so kind of what I was talking about last time was that we expect that if I do lots of experiments, that, for example, suppose I want to know whether a coin is fair or not, right? What I could do is I could keep on flipping it and I would count the number of heads and I divide by the number of total experiments, right? If the coin is fair, I expect that number to be about 50%, right? But clearly it may take a long time for my estimate like this to converge to the probability, right? So for example, let me just do a quick experiment in MATLAB. So let's go over here. So MATLAB has a random number generator, RAND, right? So this RAND basically gives me a number between 0 and 1, right? And of course, those of you that have taken some sort of computer science know that random number generation is a big deal, right? We don't want there to be any sort of exploitable patterns in this, otherwise things like cryptography and so on are bad, right? So what I could do if I wanted to generate like a coin flip, for example, is I could just say, okay, well, if this random number is truly fair, I could take the values that are greater than a half and call that 1, and the values that are less than a half and call that 0, right? So what I could do is I could say, okay, I'm going to make a random vector of, say, in this case, say 4 coin flips, okay? And now I'm going to say if the value is above 0 or above a half, call it 1. If it's below a half, call it 0. Right? So here, I got 50-50 by chance, right? And so my estimate of the probability would be 2 heads over 4 total flips would be 1/2. Well, that's great, right? If I did this again, though, in this case I got, by chance, 3 flips that were over a half, and my estimate would be 3/4, right? Which is not so good. And so the idea is, what I could do is I could make a much longer vector, which I'm not going to draw. So let's say instead of doing 4 flips, I did 100 flips, and I said, okay, I'm going to find the places where this is greater than a half, and then I'm going to look at the number of ones divided by the total length of the vector. Here my average was pretty good, right? And so I could do this again. Let's see how I did if I do it one more time. Here my average was not so good, right? So kind of what I was getting at last time was how many flips do we have to do to be within a acceptable tolerance of the true probability, right? So the kind of idea is that suppose I did, 1,000,000 flips, right? Is that 1,000,000? Yeah. And now I say, okay, what did I get here? Well, now my number is pretty good, and if I were to repeat that, I got the same thing, surprisingly. You can see now that my numbers are quite a lot better than they were before, right? And so this is kind of, again, what's known as one of these laws of large numbers that says, how much do I have to do something? And I can know that, it's very, very unlikely that if I do 1,000,000 coin flips, I'm going to get a probability estimate that's like 0.023, right? That would be, very far outside the kind of, in some sense, confidence interval I have on my measurement, right? So we're going to talk about that in some detail, later on in the class, but just to give you a preview, that this just tells us as a sanity check that the real world and probability kind of match, right? You can't cheat probability by, getting a whole bunch of random outcomes in the limit that don't kind of correspond to the true underlying distribution, right? And as we saw with the case of 4 coin flips, when you have a small number of experiments, then you have a much, less likelihood of being right on the mark, right? So that's just kind of like, hopefully, common sense. Okay, I guess what else do I want to talk about while I'm in MATLAB? One useful thing, in case you don't know it, is there's a function called n choose k. Like if I say, what does 6 choose 2? So you don't have to necessarily work that out on your own. Of course, you can't use it in the exam, but there's something like this. And there's also, I believe, there are ways of generating other random variables. So if I look for binomial in the MATLAB documentation, I should be able to find a way to generate a bunch of binomial random variables without having to manually code up probabilities. So if I look at binomial distribution, I know it's not very exciting for you guys to see. I'm not sure, actually, this could be in the stats toolbox, and we may not have it here. Let's try it here. Binomial distribution, this is about fitting it. There we go. Right, so here I can specify a, yes, bino RND. So I could say, okay, give me a random variable where I want to do bino RND? Give me 100 coin flips with a probability of success of 0.5. And that generates 49 heads. I do that again, I got 55 heads, and so on, right? So these numbers I kind of expect to be close to 50, right? But this is going to be, again, kind of like this bell curve we kind of saw last time in the Plinko game. If I were to make my probability of heads a lot greater, then suddenly I'm going to get lots more heads on each of these trials, right? So again, and we're going to talk, actually it's one of the last things I talk about how do I generate kind of an arbitrary random variable. We'll talk about that a little bit in a future class, but not right now. So let me pause and ask, any comments or questions about this? Okay. So let me just switch back for a second to my camera. So I was kind of surprised on the homework that there weren't more questions about problem number 3, which I thought was a great problem. Maybe it's because you just thought it was so easy that you blazed through it, but I think the problem number 3 was a solid problem. So let me solve it for you now, because I want to show you how it works, okay? So the question basically was, Thanos is snapping the Infinity Gauntlet, and on every snap, with probability 1/3, someone disappears, right? So basically, the probability of disappearing on snap was equal to 1/3, okay? And so you can recognize this as kind of like a geometric random variable, right? Where disappearance is success and staying alive is failure, which is kind of a weird way to look at the world, but that's the way it is, okay? And so now I can ask a question like, what is the probability that, that it takes at least 3 snaps to get rid of both Scarlet Witch and Vision, okay? And so I could tell on Piazza from the couple questions that there were that people were kind of thinking about all the possible ways that this could happen, right? And there are lots of ways, right? Because for example, like I said on Piazza, Scarlet Witch could go on snap 1 and Vision could go on snap 5. Or Scarlet Witch could go on snap 4 and Vision could go on snap 3, right? There's an infinite number of ways that this could happen. And so the better way to think about it is, what is the complement of this event, right? What are the ways this can't happen? So there are really only 3 possibilities for the complement of the event, right? So basically I have either Scarlet Witch and Vision both go on snap 1, right? I have one of them goes on snap 1 and one of them goes on snap 2. But they're both gone by snap 3, or they both go on snap 3, right? Or sorry, snap 2, right? So these are the only 3 ways that the event can't happen, right? And since everything is independent, basically, what's the probability they both go on snap 1? Well, it's 1/3 that she goes and 1/3 that he goes, right? What's the probability that they both survive snap 1 and then both die on snap 2, if they really did die? So basically, she has to survive snap 1 and then die on snap 2. He has to survive on snap 1 and die on snap 2, right? And then what's the middle probability that one survives and one stays? Well, again, there are 2 ways that can happen, right? Either she goes first or he goes first. So again, this is kind of like a combinatoric, 2 choose 1, where basically, one of them goes immediately and one of them stays and then goes, right? And I'm not going to multiply this all out, but basically it's 1 minus this minus this minus that, right? All right, but that wasn't my best work. My best work was problem 3b, which I thought was a great problem. So problem 3b was, what's the probability? So let me pause and ask, any questions about this? Okay. So next question is, what's the probability that Thor goes before Black Widow? Okay. So again, there's an infinite number of ways that this could happen, right? And you can't get away without kind of characterizing all of those possible ways, right? But there are a few ways to think about it, right? So the way that I first thought about it was that, there are 3 possibilities. There are 3 kind of ways to divide up the sample space, right? Either, so here's the sample space, right? So either Thor goes before Black Widow, or Black Widow goes before Thor, or they go at the same time, right? That was the way I first thought about it. And so it seems pretty obvious that Thor going before Black Widow and Black Widow going before Thor have to have the same probability. There's no reason why those would be any different, right? So if I compute the middle guy, then I can say 1 minus that divided by 2 gives me the probability that I want, right? So what's the probability that they go at the same time? So the probability that they go on the same snap is basically the sum. I have to sum up these infinite possibilities, right? From I equals 1 to infinity, the probability that they both go on snap I, right? So that basically means that for each of them, they each survive I minus 1 snaps, and then they both go on snap I, right? So it's like saying that they have 2/3 to the I minus 1, they survive, and then 1/3 to the I, and then that happens to both of them, right? Because everything is independent. So let's work out what this number is, right? It looks kind of messy, but it's not that bad. So I have sum from I equals 1 to infinity. I'm going to bring out this 1/9, which is this 1/3 squared, and then I have 2/3 to the I minus 1. And then I can kind of renumber this to be from I equals 0 to infinity, 2/3 to the I. This is your old friend, the geometric series, right? So, oh, I'm sorry, this is 2/3 squared to the I, my mistake. Right? So it's like this. Sorry about that. Let me be clear here. So it's like 4/9 to the I, right? Because I've got 2/3 squared to the I minus 1. And I took the 1/9 out. Right, so now this is going to be 1/9, 1 over 1 minus 4/9. So that's going to be like 1/9 times 9/5, which is 1/5, right? So that means the probability of being in this possibility is 1/5, and then that must mean that it's going to be 1 minus 1/5 divided by 2. So that means I have 2/5 probability of this, 2/5 probability of that. Okay. So the answer is 2/5. But let me show you a different way to get to 2/5. In case you don't like this kind of appeal to symmetry, right? Let's just do it directly, okay? So let's suppose instead that I kind of enumerate all the possibilities in which this could happen, right? So what I could have is this probability. What are the possible ways this could work, right? So I could have, so I want Thor to go before Black Widow, right? So basically, the first way this could happen is that Thor goes on snap 1, and Black Widow survives snap 1, right? Or I could have the probability that both survive snap 1. Thor goes on 2, Black Widow survives on 2. And then kind of keeps on going like this. Both survive 2, dot, 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 right? So again, let's see the pattern. So Thor going on snap 1 is 1/3. Black Widow surviving snap 1 is 2/3. Both surviving snap 1 is 2/3 squared. Then Thor surviving, I'm sorry, Black Widow surviving is 2/3. Thor being disappeared is 1/3. And then that kind of goes on like this. So basically, at every step, I have another 2/3 to the squared multiple. So now I can see that, again, this is going to be, I've always got this common factor of 2/9, and then I've got the sum from I equals 0 to infinity of 4/9 to the I, which is going to be 2/9 times, 1 minus 5/9. This is the same 2/5 that we got before, right? All right. So if you got this problem, you can feel good. If you didn't, it wasn't that easy, was it? I think it was a good problem, though. So again, study from this. Question? Could I pull up the other page from the first way of doing it? Like this?